I made this demonstration to compare various relative operations. If in the default case, this is trying to find the Lorentz transform within this. There's a x and an x prime and a t prime. And what exactly are those? And that's a question that I'll get back to. The first is I started to draw the clocks of the relative frames, which are pretty important, but I won't try and dwell on those too much. The ship is moving at some velocity to the right, up to the speed of light, and it contracts. And I can go positive or negative to the speed of light. And then this is an observer, so they're at this position, and they're always, they're not moving. So in the Lorentz transform, that would be a vertical line, which I can shift the frames. And then this is the ship's clock and how far and where it is, but it thinks it's always in the same position. But the observer is moving backwards, and this is its position in its time. I can change the observer's velocity, but that's not fully implemented, so I'm not going to dwell on that either. The length is how long the thing is. It's standardized on 1 light second. The units are feet per nanosecond, which is approximately the speed of light. This is... I should set this to 0. This is a distance in the up and down direction, forward and backward, that between the observer and this. It changes how close it can actually be, because there's a minimum distance then. There's a run length, which we can extend. This is... wanted to compare what the clocks were. So this is the ship's clock. It's local now. What it sees from the front and what it sees from the back of itself. So there's a slight time delay if there's a velocity. That the front is newer. This is older is towards the back, and newer events is towards the front. So this is a time after this one. This line is now. This is where the ship observes itself to be. If it was, still moving. So its absolute position in its time scale control where it is. And if it's going 70% the speed of light, or 0.707 the square root of 2 over 2, then the ship feels to itself like it's going the speed of light, because it's going forward 0.707, and the time dilation on its clock is only making it go forward 0.707. So it's 1 unit of time, and 1 unit forward is the speed of light. And if it goes any faster than that, it can go actually many times the speed of light. So this is like 2 times, 3 times, 4 times, a lot times the speed of light. But that's because its clock is running so very slow. It's not actually going the speed of light. And this is where the observer actually sees it. So this could be an x prime. This could be the x prime. But I'll get back to that anyways. This is, if I reduce the velocity some, and turn off the ship local. This is the time places that the observer sees this ship. So its position is where the ship was when it emitted that signal. So it sees a older version of the front and a newer version of the tail. So this line is actually skewed in time, that this is new and this gets progressively older as it goes along. And this is the time that is seen from the front of the ship. This is the time that's seen from the back of the ship. This is the time that the back of the ship sees to an observer that's in the ship. You can change that offset so the time changes where he is. See, if he's further back, if he's further like this distance, then he sees the front and back clocks at the same time. If he's exactly like negative the speed of light backwards in feet, then he sees the clock synchronized on the front and back wall. So if he was in the center and it was stopped, then the clocks are the same on the front and back of the wall. This is what the observer sees of now. This is where this ship sees the observer at, this blue line. So if we go backwards in time, he sees us further back than we actually are, because we're moving in time forward. But this is an older version of us, but since our position never changes, it's still just a straight line. And you'll notice that when the ship is approaching us, there's actually an elongation, that this time is stretched across a long diagonal of the ship. See if it doesn't really track within the bars. Around as it's passing you, it inverts and goes shorter and contracts. But there's a length expansion that's seen here, that the ship should be drawn on this red line, stretched longer than it is, even though it actually has a contraction. Similarly here. This is after being contracted. This is how big the ship actually does appear. The contraction does shrink that relatively too. And this should be times 2 of its length. And then this should be down to 0 of its length, but before it's too, I don't know, something like that. This is something like the Lorentz Transform. This is how space actually sort of does transform. The green line tracks in between 2 red lines and stays on the yellow lines as the as the offset changes, and it's before and after the observer, and as the velocity increases. No. So these are more elongated, but it's not in an exact now. There's no straight, it's not between 0 and 1 really here. So this isn't really a meaningful Lorentz transform. It shows you what it would look like, but not where it actually is. The the final sort of test that I had was this remote galaxy. That if the ship is in between the two at a certain position, which is exactly in the center of the ship sees now on the opposite sides of the ship, there's an offset. And velocity now. So this should be 0. So if two events happened in a distant galaxy and on Earth, and there was some distance in between them, probably more than 10 light years, or 10 feet, but it doesn't really matter. If you're offset in the ship slightly, that's this back, then you see... No. The back is the red line, and the front is the blue line. This should have been reversed. The front of the ship sees a newer version of the Earth than of Andromeda, and the back of the ship sees a newer version of Andromeda. And if you were to back up time a little bit, then the front of the ship can see the same time, and if you advance time, then the back of the ship can see the same time. And the question is, if an event happened simultaneously somewhere in Andromeda and on Earth, and you had an observer traveling at some speed, what could he say about the event? And to see this event to see that event simultaneously, he would have to be automatically in the middle. And if he was slightly offset to the left, then he's going to see newer Andromeda from the older Earth. So in a previous time, he's going to see the event from Andromeda here, and then later see the event from Earth here. So you could say that breakfast happened before Earth. Breakfast happened in Andromeda before Earth. And that's related to this exam question, which is let's see if I don't scroll. While you're having breakfast in the morning, a creature in Andromeda galaxy is doing the same thing, and we call the two breakfasts X event on Earth and event Y on Andromeda. Simultaneously means in your reference frame. So whatever your wall clock is, simultaneously across the universe, he's doing the same thing. So if instead we describe the two events in another reference frame of a space traveler at very high speed towards Earth, which of the following is true? And this is an observer traveling at a high speed. It could be a higher speed, but it's high enough. Between Andromeda and Earth, what can they say about it? And they could say that one event happened before the other. They could be offset in the other direction and say that, the event in Andromeda happened before Earth, because as he goes further, or this one, he would say Earth happened before Andromeda, because Andromeda event hasn't been seen yet. Or you could say that they happen simultaneously. So which of the following statements is true? A and B are simultaneous. X is before Y? Sure. Y is before X? Sure. Question is not well defined. We cannot define simultaneously that do not occur in the same place in space. Well, it was defined up here in the question that simultaneous means in your frame. So it's not D, but it could be A, B, or C. You could draw... Ignore this left-hand side. You could draw the two events that they happen in Andromeda and Earth, and they have a certain light cone. And when a ship passes a place in space, that's the X position, in a place and time, that's the y position, they see that appropriate event. Like, the event from Earth will have traveled this far and been at this position when the ship was. So it could see Earth first and then Andromeda. Right at the plus, it could be both. This is Andromeda first and then Earth. If the ship left after the breakfast happened on Andromeda, then you'd actually only see the Earth, but you'd never see anything else. The correct answer to this, using the Lorentz transform, is this B answer, that the event on Earth occurs before the event in Andromeda, which is locked at this center point. And this is, I mean, you can demonstrate easily that an observer can see any of those, so doesn't that sort of mean that the math is wrong? But to go back to the clocks, there's this page that describes the clocks. It has a link to that and all the various stuff on it. So it could be any of these things. Let's turn off the distant frame. So I could have a velocity that's very high and feel like I'm going faster than the speed of light. I can adjust this so that the observer's frame is doing the same thing, but this is offset. I can unoffset this. This controls the ship's offset too. That's why these lines are changing. But then this position is where it sees, where it knows this observer is. This isn't where it sees that observer. I mean, this is where it sees it. Because it's translated a long time back in time. But this is where it knows it is, because similar to it knows its position is here, and it knows its own clock is here. But this is what the observer sees. These don't translate with the prime bias. Prime bias is to move between x and x prime and t prime in that Lorentz transform. Because this is my clock and my position, and this is their clock and their position, or their velocity. So ideally that's the transform, that's what the transform should sort of look like. But I can't transform using Lorentz past the speed of light. There's no idea that there is a thing greater than the speed of light. The length expansion, I need to slow down some. The length expansion is never mentioned. But we'll move on. I went to review some videos. This was a good one. This is the Lorentz Transformation, the Mechanical Universe version. They have this 3D plot that this event is, this is the stationary observer. This is the moving one with detectors on its end. But this one also has, when they pass each other, a pulse is emitted from the center and then hits detectors here, hits a detector here. And there's two detectors on this end, and then once they hit the detectors, then the observer sees the detectors. So it doesn't really know about the photons. But this is the natural frame with the train moving, and the person sitting still, and the light cone is untransformed. And then this is the other way. Well, no, this is just that these two events should be simultaneous for what's on the train. Um, so if we can switch those two events to be simultaneous on the train, and then these two events that are outside get transformed, so one happens before the other, much like this is seen. Because as the train is going by, I'll get back to that. But between these two, the light cone isn't transformed. And with a one-way speed of light, the light cone has to be transformed for the moving observer, because his light cone is just different. He's going to pick up photons from a different place at a different time. Light relative to him is different. This is all predicated on one speed of light. There's one speed of light ever, no matter which direction it's going, no matter what the observer is doing. But if the observer is moving relative to that direction it was emitted from, its relative speed may seem different. It would be perceived differently. So at no velocity, you have a light cone like this. There's no light cone into the future because nothing's happened yet. You can only see things that have already happened. If you're moving 0.9% speed of light, 90% of the speed of light, then the cone you see is more like this, and things behind you cover more space in less time. There's a very short amount of... You can even go... This function even goes faster than the speed of light. So you see an arc still ahead of you, but what's behind you you don't see. And you see an echo of things that were already past you. In the time leading up to you, they emitted signals and photons and information that you don't see until after they pass you, and once they pass you, you see them going backwards in time, backwards away from you. The other part of that demonstration was the waves, which I added. This length contraction option is more of a debugging option than it's required for anything to actually work. But this controls based on the velocity. So at zero velocity, waves from the front to the back, and waves from the back to the front, and waves side to side are all basically the same. As you accelerate, there's fewer wavelengths ahead of you than behind you, because when you're moving ahead, there's lots of pulses that are emitted. Even considering that this is time contracted, so the pulses aren't emitted as fast because of that length. The two-way sum, the number of waves here and the number of waves here is 40. And the number of waves side to side is 20 one way, and then two way is 40. So for any velocity, the bottom waves don't change, and they do have a velocity calculation applied to them. It's just cancelled out because of length contraction and time dilation, time contraction. And this is length contracted, otherwise there would be many more waves here, and things like LIGO wouldn't work. But with the two-way message, there's exactly 40 wavelengths in the air, so you know exactly, it's that long, no matter how you count it. So if you're measuring in wavelengths, if the ship is moving forward, I don't know which one of these. This one. So as the ship is moving forward through time, it runs into this front signal faster, and the back signals pile up more and more. But also from the back, because these are contracted and are look blue shifted, but because the detector is also moving away from these, then it elongates these back to the normal frequency. Similarly here. So in a one-way situation where you have an event that happens and then immediately a detector, if that whole thing is moving from the front, it's redshifted from the emitter and corrected by the detector. And the other way, if it's emitted from the back and moved this way, this is blue shifted, and then the emitter, because it's moving away, red shifts it back to green. So it sees the same frequency forward, backward, left, right, as long as it goes forwards. I mean, even in a one-way trip, there's no frequency difference. But there are fewer waves, but you can't necessarily count that. Because any distance is a proportional amount of waves. If I increase the length, I'm not calculating length with that. But length is just going to scale everything linearly. It's not going to be any different. Okay. And yeah, that's all my approach to try and get to this Lorentz transform. Which their situation is this. That at time 0, there's 2 detectors. I didn't mark where they actually were. This is what the ship is seen as from the observer, and this is what the observer is seen as from the ship. And the line ends up staying in that well, no, this isn't the observers on the ship. This is observers at 0. So at 0, a pulse is emitted that goes out to 2 detectors, and it hits the back of the train's detector, which starts a red pulse here and a red pulse here, and then keeps going out, and then hits one of the both green detectors really at the same time. This is going to keep going until it hits the other red detector. And then this hit both green detectors. But it actually hit, and it hits both green detectors at the same time. But the current time on this clock is slightly contracted because his watch is running slower. And then those green signals come back to the observer, and then they hit simultaneously and go away. So the observer sees this exactly at 2 seconds. This was 0, 1, 2 seconds. And this one, it hasn't gotten to 2 seconds yet. There's still more time left on its clock. But it knows that we saw them simultaneously at this time. And then, well, I guess that's when it sees it. It's not that we saw it. This isn't actually about him seeing anything. This is all this observer's perspective, and this is all this observer's perspective. This green line is just from this drawing, from this video. This sloped line is this sloped line. And so at 2 seconds on its clock, it sees the events from both detectors at the same time. Score. I'm exactly with relativity. And then later, this guy sees the detector from the back of this ship. Very delayed. And then eventually and then the other one sees the back detector from the first ship. And these are all at exactly the same times, relatively. This is a dilated clock, though, contracted clock. Can change the lengths, can control the velocities. So you can see that generally it looks like a hyperbolic transformation. Because I could just skew either one the other way, right? And then, but the problem is, these aren't exactly mirrors of each other. There's a distance of 2 here, or 1.4. There's a distance of 2 here, but then this goes out almost to 2, while this is not quite as far away. And that's because in this case, when his event is generated is not at exactly the same time. That, when the detector actually fires. When he sees it is exactly 2 seconds, no matter what speed he's going. The other guy's detectors in the moving frame, or the stationary frame relative to the moving frame, they're out of sync. And this is what the Lorentz Transform is really trying to capture. Is this transform, but this is the observer's clock at real position, and because this is ground observer is never contracted. If I go really, really fast, this ground observer is still just 2 seconds away, while this observer is much further away, because it takes longer and longer to get to the front of that ship, even though the ship is contracting. If the relative distances that these events are marked at and the positions that they mark in space is different than looking at it the other direction. Because this distance that's elongating is this constant distance. But this distance doesn't elongate just because this guy's going fast. And that's what that real issue is. I only draw the stationary observer long enough for him to generate the light events, and then the E goes away. So to walk through this again. So the light pulse is emitted, hits the back detector, hits the front and back detector. The ground observer already saw the train's rear detector because it was hit at a position greater than 1. And then this guy sees the front detector because he's passing near it, very close to it because of his speed. And then the stationary observer sees both of his events at the same time, and then the moving observer sees both of his events at the same time, and then eventually they see the other events at the same time, but in different places, from different places. So the Lorentz Transform doesn't capture what reality is, apparently. Links and descriptions and all kinds of stuff, more words, are in the description down below.